Hey everyone, and welcome. Today, we're diving into a piece of medical tech that does something truly incredible. You see, we're all familiar with things like X-rays, which shine radiation through you to take a picture. But what if a camera could capture radiation coming from you? What if it could see not just the shape of your organs, but how they're actually working in real time? Well, that's exactly what the Gamma camera does. Let's get into it.
Okay, so really think about that for a second. An X-ray is great for showing you if a bone is broken, right? It shows you the structure, but it can't tell you how well your kidneys are filtering blood or how your heart is pumping. So how on earth can a camera see function? How can it possibly capture biological activity? That's the big question we're going to answer.
The secret, the whole magic trick, starts with something called a radiopharmaceutical. It's basically this super clever cocktail. You've got a drug that knows exactly which organ to go to, say your thyroid, and it's combined with a little radioactive tracer. Once it's in your body and gets to that organ, the tracer starts emitting these tiny, high-energy particles called gamma photons. And here's the key part. Instead of the machine being the source of radiation, you, the patient, briefly become the source, like a little beacon broadcasting signals from the inside out. All right, so our patient is now emitting these signals. Let's start our journey and see how the camera even begins to make sense of all this information that's flying its way. And right away, we hit our first huge challenge. That radiopharmaceutical is sending out gamma photons in every single direction. I mean, it's a total storm of energy. If you just try to capture all of that at once, you'd get nothing but a chaotic, useless blur. So to create a real image, the camera has to somehow tame this chaos. It needs to bring some order to the storm.
So how in the world does it manage that? Well, this brings us to the first and honestly one of the most critical parts of the whole camera. Think of it as the gatekeeper.
Okay, so this diagram here is going to be our roadmap. It shows us the guts of the camera. We're going to follow just one of those little gamma photons on its adventure, starting right from the bottom, closest to the patient. The very first thing it runs into is that piece called the collimator.
Right, so you can imagine if the camera just opened its eyes to everything, all those photons flying in from every which way, you'd get that big, useless, blurry mess we were talking about. The whole game here is to filter out all that noise and only pay attention to the photons that are on a direct, straight-shot path to the detector.
And that, my friends, is exactly what the collimator does. It's basically this thick slab of lead, which, is awesome at stopping radiation, and it's been drilled with thousands and thousands of tiny, perfectly straight tunnels. Any photon that comes in at an angle, bam, it gets absorbed by the lead walls. Only the photons that are flying perfectly straight down one of those tunnels get to pass through. It really is the ultimate bouncer at the door.
Okay, our little photon successfully made it past the gatekeeper. Phew! But now it's about to go through this incredible transformation from something totally invisible into actual visible light. So after zipping through the collimator, our lone photon slams into the real heart of the detector, this big, beautiful sodium iodide crystal. This is where the magic really starts to happen. So what's going on inside this crystal? It's really a simple three-step dance. First, that invisible gamma photon flies right into the crystal. Step 2, the atoms inside the crystal absorb all of that photon's energy. And then, step 3, almost instantly, the crystal spits that energy back out. But this time, it's in the form of a tiny visible flash of light. We call that a scintillation. So just like that, zap, an invisible gamma ray becomes a tiny, visible spark of light. All right, so we've got a flash of light. Awesome. But how does the machine even see this super faint little spark? And maybe more importantly, how does it know exactly where inside that giant crystal the flash happened?
I mean, this is a huge challenge, right? We're talking about a microscopic flicker of light inside a big crystal. Pinpointing its exact location is absolutely crucial if we want a sharp image and not just another blur.
Well, the answer comes in the form of these amazing things called photomultiplier tubes, or PMTs for short. Just imagine them as an entire grid of super sensitive electronic eyes, all packed together right behind that crystal. Their only job 24/7 is to sit there and wait to detect even the faintest glimmer of light and turn it into an electrical signal. So how do a bunch of eyes find one exact spot? It's genius, really. See, when that little scintillation happens, the light spreads out and hits a bunch of different PMTs. But, and here's the trick, the tubes that are right on top of the flash see it way brighter than the ones further away. A computer, in a split second,
looks at the signal strength from all the PMTs that saw the flash, and by comparing how bright it was for each one, it can triangulate and calculate the precise X and Y coordinate of where that flash happened.
Okay, so we've just followed the incredible journey of one single photon, from inside the patient all the way to becoming a single coordinate on a computer screen. But how do you get from that one tiny dot to a whole, detailed medical image?
The answer is so simple, but it's really powerful. You just do it millions and millions of times.
That whole journey we just traced, it happens again and again and again, millions of times over a few minutes. Each individual photon gets filtered by the collimator, converted to light in the crystal, and then precisely located by the PMTs and the computer. Each location becomes a single dot or pixel on the screen. And as these millions of dots build up, an image starts to form. Areas where the organ is really active and working hard will send out more photons, so they'll get more dots and look brighter. So the final result isn't just a flat picture of an organ. No, it's so much more. It's a living map of how that organ is actually working.
And this amazing core technology is the engine behind a couple of different types of scans you might hear about. The standard, flat 2D image is called planar scintigraphy. That's our map of function. But you can also get fancy. You can have the camera slowly rotate all the way around you, taking pictures from every angle. A computer then takes all those flat pictures and stacks them up to build a full 3D model you can slice through and look out from any angle. That's called SPECT imaging.
And this right here, this is why any of this matters. This isn't just some cool physics experiment. It's a tool that genuinely saves lives every single day. Doctors use it to see exactly how well a patient's heart is working, or their kidneys, or their thyroid. It's essential for bone scans that can find tiny fractures or diseases that X-rays might miss. They use it to hunt down tumors, find hidden infections, and to get a clear picture of blood flow deep inside the body. It's absolutely vital.
So there you have it. We've gone on this wild ride, from an invisible gamma ray popping into existence inside a patient, all the way to a detailed, functional map on a doctor's screen. It's a technology that literally lets us see the invisible energy of life at work. It really makes you wonder, right?